go. Make sure that I'm recording from the right channel. Yep. This is all working. All right. We started with line 1. Okay, that's not surprising. What does it do? Line 1 is an assignment statement. I get 0. So we should know that by now. Line 2 is the beginning of a while loop. So we have to evaluate the condition. We need a little bit more space for comments in this case because our condition is a little bit long. I is less than bar A bar. Is that true or false? What is bar A bar? A number of elements in the array, and how many elements do we have? We have 3 elements, so bar A bar evaluates to 3. 0 is less than 3 is true. Can we make a conclusion about the conjunction at this point and say, oh, the conclusion of the conjunction is true or false? Can we make a conclusion? Not yet, okay? Because true and anything is anything. So we have to evaluate the other side of the conjunction. The other side of the conjunction is A bracket I does not equal to K. A bracket I does not equal to K. Is that true or false?
True.
It is true because A bracket I is A bracket 0 because I is 0 at this point. A bracket 0 has a value of 5, and K has a value, has a constant value of 1. 5 is different from 1 is true. So now we have true and true, which is true. So the entire expression is true. We have to go into the loop. We perform whatever is specified in the loop, which is I gets I plus 1. I goes from 0 to 1, and then where do we go?
2.
We go back to line 2, because at the end of a loop, we go back to the beginning. In this case, the beginning of the loop will also ask the question again. I is less than bar A bar. Is that true or not? I is 1, bar A bar is still 3, so I is less than bar A bar is true. We cannot conclude whether the whole thing is true or false, so we have no choice but to look at the second condition. A bracket I is A bracket 1 in this case because I has a value of 1, which has a value of what? It has a value of 1. 1 is different from 1 is false. True and false is false. So the entire expression is false, and we can get out in this case. Are we doing okay so far? Okay. So we'll go ahead and save this file into today's folder. Let me create a folder first. This is a search algorithm. All right, let's go ahead and create our second scenario. I'm just going to copy and paste into another sheet. But this time we'll make use of the lazy evaluation. So the program is not going to do anything that's dangerous. So we'll look for a value that is not in the array. Well, there are plenty of values to choose from. 2 is not in the array. And we'll go back to sheet 1 to look at the algorithm, look at sheet 2 for the trace. Line 1 still does the same boring thing as last time, which is initializing I to 0. Line 2 has to evaluate the condition. I is 0, bar A bar is 3, 0 is less than 3 is true. We cannot make a conclusion yet. We have to look at the second part or the other part of the conjunction. A bracket I is A bracket 0 because I has a value of 0, which has a value of 5. The element has a value of 5. 5 is different from K, which has a value of 1, is true. True and true is true. This part is almost identical to the last trace. We go to line 3. Line 3 is adding 1 to I. I goes from 0 to 1. We go back to line 2. So this time it is still true because I is now 1. 1 is less than 3 is true. A bracket I is A bracket 1. A bracket 1 has a value of 1 just like last time, but k this time has a value of 2. 1 is different from 2 is true, so once again we have true and true. Then we move on to line 3. We add 1 to 1. We have now 2 stored in I. We go back to line 2. And this whole thing is still true because I is 2, 2 is less than 3 is true. And A bracket I is referring now to A bracket 2. A bracket 2 has a value of 3. 3 is different from K, which has a value of 2, is true. So we have true and true again, and the entire conjunction is true. Once again, we go to line 3, and I is now incremented to 3. Now we go back to line 2. This is the iteration where things get a little bit interesting, because when you evaluate the first condition or the first comparison, I is 3 already, bar A bar is also 3. 3 is less than 3 is false. When you have a conjunction and you confirm that the left-hand side is false already, do we have any way to conclude for the entire conjunction? Because false and anything is false. Okay, so it's kind of like 0 in multiplication, right? Because 0 times whatever is 0. So in this case, I already know the entire thing is false, so I don't even bother to write down the second portion, and I just say that this is already false, which concludes the entire conjunction is false. In other words, we are being lazy because we are not evaluating the right-hand side when we don't have to evaluate the right-hand side. In this case, laziness is a feature. Why do you think it is a feature? What if I was not lazy and I go like, oh, I better check the other side too, even though I know the entire conjunction is false. I want to check the second side. What would happen if I were to check the right-hand side?
It goes forever.
Well, it depends on the programming language, but I'll be referring to A bracket 3 because I has a value of 3 right now, but the array doesn't have A bracket 3, it only has up to A bracket 2. Now we already kind of explained, in different programming languages, it will do something differently. In C and C++, it will go to a location that does not belong to array A and just say, I'm just pretending that this is a part of array A and use that value for comparison purposes. In Perl, PHP, and other scripting languages, it will make the array big enough so that A bracket 3 will exist with a default value. In Visual Basic, it will give you a runtime error and say, oh, we are accessing an array out of bound on this line right now, which in my opinion is the best response, because it's stopping the program exactly where it's supposed to stop instead of giving you a silent error in C and C++. So in this case, it is a feature. Let me save this program. What if we don't have short-circuited evaluation? In other words, what if the conjunction will continue to evaluate the other side all the time? What are you going to do? We are kind of lucky that all modern programming languages have this particular feature so that we don't have to worry too much about it. But what if they do not? What do you have to do to implement the same logic? You will need to separate the two comparisons. Okay? So when we look at this code here, what you have to do is to make sure that this portion and this portion do not appear in the same conjunction. So you have to separate it into two different places. So what we'll do now is to save this program as a different name so that we can discuss what the code would look like without short-circuited evaluation. So we'll have to delete, or no, I guess we can change it later. Okay. So without short-circuited evaluation, one easy way to deal with this problem is to introduce another variable. But this time, the variable that we are introducing is going to be a Boolean variable. I will explain exactly what a Boolean variable is. Okay, so we'll say this variable has a name of found, and it is initialized to false. How is this assignment statement any different from all the other assignment statements that we have seen so far? It's not a number on the right-hand side. Instead, it is a Boolean value. but is the concept any more foreign than the original assignment statements? Nope, we still have a variable on the left-hand side, we still have an expression on the right-hand side, and the variable is updated to whatever the value is specified on the right-hand side. So it works the same way, it's just that it's no longer storing a number, it's now storing a Boolean value, which is either true or false. So now, what I can do here is I'm going to change this expression so that we are not doing the comparison in the conjunction itself. I am simply referring to found. And in the convention in this class, we always have a do at the end, which is not really necessary, but we'll put it here. And we also need one additional row here to basically set the value of found. Because if we do have an element in the array that has the value of k, we want to update found to reflect that. Okay? So if we want to update found, we know that found has to be on the left-hand side of the assignment statement. What do we specify on the right-hand side? Well, if we do something like this, then it will just say, yep, we found it, without any confirmation. Okay? So what do we need to do to confirm that, yes, we have found an element? Can we do a comparison? Okay, let's think about this. What do we need to compare in order to confirm that an element in the array has the same value as k? The comparison will be between k and an element of array A. But which element of array A? The one with an index of I. Okay? So do we know how to do comparison? A bracket I equals k, just like that. Now we haven't seen anything like this before because we always put a numerical value in the expression. With this particular statement, the only big difference is this is not going to give you a number. It's not going to give you a numerical value. Instead, what is it giving you? A Boolean, a true-false value. But nonetheless, it is a value that you can store. Are we still doing okay so far? Is the use of found consistent? Am I using found always to store a true-false value? Am I always using it as a true-false value? Where am I using it? This is just changing it. Where am I actually using the value of found? On line 3, in the conjunction. Go ahead.
You can't use a while loop in this specific case.
Yeah, I can.
Well, the first time it tries to go,
It is
found
already
will be false, which
yes.
means that the loop won't execute. Because even...
Oh, and not found, sorry. You're right. Very good. Good job. You caught it. The trace would have caught it too. Because it makes sense, actually when you read it, it makes sense. It's basically saying as long as we haven't seen everything in the array and we have not found what we are looking for, bump up the value of I and also see if the current element that we are looking at has the value that I'm looking for. Very good. Good point. Are there any questions at this point? We'll go ahead and trace this code and we'll see how it works. So we need one more variable now, which is found. And we'll keep everything else about the same. Erase the rest of the trace. Let's start on line 1 again. Any questions? Okay. So line 1 will still do the same thing. I gets initialized to 0. Line 2 now has to initialize found as a Boolean variable to false. Line 3 is now a little bit simpler than before because the first one is just I is less than bar A bar. The second one is not found. Is I less than bar A bar? I is 0, bar A bar is 3, so I is less than bar A bar is true. What about not found? Found has a value of false. Not false is true, so we actually end up with true and true, which is true. We go to line 4 now because we now have a line 4. how should I update the value of found? A bracket I equals K. It is false. Very good. Okay, because A bracket I is referring to A bracket 0 because I has a value of 0. A bracket 0 has a value of 5. 5 equals 1 is false. And that's why found is going to get a new value, quote unquote, new value of false. Okay? When you trace something like this in your program, you have to update. This cell is important because we are actually putting a value into the variable. It just so happens to be the same as what it had already. But you do have to indicate that there is an update operation at this point of the execution of the program. We go back to line 3. What about this time? Is the whole expression true or false? I is less than bar A bar is true because, oh, I forgot one thing, didn't I? I have to go to line 5 now. There are 2 lines in the loop. Line 5 is just adding 1 to I. I goes from 0 to 1. We go back to line 3 after that. I is now 1. 1 is less than bar A bar, which is 3, is true. Now we have to evaluate the second side. Found itself is false. Not false is true. So now we end up with true and true again, which is also true. And then we go back to line 4. Line 4 will try to set the value of found again. What is it this time? True. It's true because A bracket I refers to A bracket 1 because I has a value of 1. 1 equals 1 is true. So the right-hand side of the assignment statement is true. The only thing we have to do is to store that to the variable specified on the left-hand side. So found will now have a value of true. We go to line 5. Line 5 is I gets I plus 1. I now has a value of 2. Then we go back to the beginning of the loop, which is line 3. Is I still less than bar A bar? That's true because I has a value of 2. Bar A bar is 3. 2 is less than 3 is true. What about found? Found has a value of true, but what is not true? Not true is false. True and false is false. So this entire expression will give you false. What do we do when the condition of a loop is false? We get out of the loop, we get to post, and we're done with this trace. So it works in this case. What about this one? Remember, we have 2 cases. So we want to kind of double check and make sure that it works in both cases. So once again, we'll go ahead and change the sizing of the columns a little bit. And start from scratch. Okay, line 1, you're still doing the simple thing. You're changing I to 0. Line 2, we'll change found to false. And I forgot to put a question mark here and also in the previous slide. So I kind of broke my own rules. Get back here. Okay, we are on to line 3 again. I has a value of 0. 0 is less than bar A bar, which is 3, is true. We evaluate the second condition. Found is false, not found is true. So we have true and true again, which is true. We go to line 4. What should I set in found in this case? A bracket I equals K. I equals to 0. The whole thing is false. We go to line 5. We add 1 to I. I goes from 0 to 1. We go back to line 3. This whole thing is going to be true again because I is 1. 1 is less than 3 is true. Found is false. Not false is true. So we have true again on the right-hand side of the conjunction. True and true, once again, is true. We go back to line 4. How should I set the value of found this time? False. It's false because A bracket I refers to A bracket 1. A bracket 1 has a value of 1. 1 equals 2 is false. So once again, I'm updating the value of found to be false. We go to line 5. We add 1 to I goes from 1 to 2. We go back to line 3. I has a value of 2. 2 is less than 3 is true. Found is false. Not found is true. So once again, we have true and true, which means the entire thing is true again. We go back to line. We go to line 4. What do you think is this value, or the quote-unquote new value of found? It's false because I is 2. So A bracket I refers to A bracket 2. A bracket 2 has a value of 3. 3 equals 2 is false. So once again, found is false. Then we go back to line 5. We go to line 5. Line 5 is going to add 1 to I. I goes from 2 to 3. And then we go back to line 3. Now we have I is less than bar A bar. Is that true or false? It is false now because I is 3, bar A bar is 3. 3 is less than 3 is false. But remember, this time we don't have short-circuited evaluation. We always evaluate the other side also. The question is it going to do any harm? Well, let's check. What is found? Found is false. Not found is true. So now we have false and true, which is the whole thing is false. But I'm not triggering any problem, is it? And that's because I have isolated the other part, which refers to an element from in the array, is no longer in the same expression as the checking of the boundary of the array. Which version do you like better? This one or the previous one? The previous one, right? Let's bring that up again because we like it better. But there's one potential problem with the previous one. As much as we like it because it is lazy, and this time lazy is good, there's one problem with that approach. A potential problem, not a problem, but it's a potential problem. I'll just ask you one question, and you can answer that question yourselves. What if I am to change the order of these two sides of the conjunction? Instead of checking I is less than bar A bar first, I check A bracket I does not equal to K first. It's not going to work, right? So this means, what we learned in a math class about conjunction being commutative is no longer true in programming. Does everybody understand what is commutative in algebra? Give me one example. Just in normal arithmetics. Go ahead.
2 plus 3 equals 5.
2 plus 3 equals 5, but it's also 3 plus 2. We can change the operand of an operator without changing the result of the value. Now, in a math class or a logic class, if you have two booleans, and let's say x is a boolean and y is a boolean, x and y is technically the same thing as y and x. The order does not matter from the math point of view. But in a programming point of view, it does matter because we use short-circuited evaluation. So in the case like this, in our program right here, if you change the order of these two sides or swap the order of evaluation, this doesn't work anymore. So you have to be very careful when you are in a C and C++ class, because you will see a lot of loops, a lot of pseudocode that looks like this, and it does depend on the order of the operand, which one is on the left-hand side, which is evaluated first. Okay? When you look at a compiled language like C and C++, a lot of times it will tell you that the actual order can swap internally. In other words, the compiler can decide which way is more efficient to do something. Should I evaluate the right-hand side first or the left-hand side first? With the exception of conjunction and disjunction, because in those cases, it always evaluates from left to right. Are we doing okay so far with the concept of short-circuited evaluation? We good with that? Okay. So I saved that code already, and we are basically done with the concept of short-circuited evaluation. And we'll move on to this new slide, which is a continuation of the discussion of arrays. But this time, I'm telling you ahead of time that the array is already sorted. Do you think that will help in terms of how much time you have to spend to look for a particular item, or to confirm that something is not in the array? Yeah? I think it helps a lot. Okay? I think it helps a lot. There's a particular search algorithm that helps, that is really the trademark of a smart algorithm. What is the world population now? 7 billion plus, okay, 7+ billion. all right, which is a lot of people. So let's just say that I have one global phone book, okay? Maybe it's some kind of directory. It has everybody in this particular directory, and they can sort by ID number or last name or first name. I don't care how it's sorted, but it is sorted by the search criteria that I'm going to use. How many times do you think I have to compare whatever I'm looking for, whoever I'm looking for, with an entry in this directory in order to confirm that somebody is not in the directory? It's sorted, by the way. And I want to guarantee. I don't want someone to say, oh, what I'm looking for is past the last entry of the phone book already, so therefore that person cannot be in the phone book. I think in general, okay? How many comparisons do I need to confirm something is not a part of a 7 billion plus item array?
7 billion.
7 billion? Okay. Well, a linear search algorithm can do that with 7 billion comparisons. Any other guesses? One. Okay.
Depends on the.
It depends, but I want a guarantee. In other words, I want someone to give me a number, let's say n, and we can guarantee that within n comparisons, we can confirm an entry is not in the array. So one is not a guarantee. Square root. Square root has nothing to do with it in this case. But you guys are getting warmer. You're thinking in math operators now. Yep.
Is it n minus 1? Someone said it back there.
N minus 1, so that would be 7 billion something minus 1. No, it's a lot smaller. Numbers a lot smaller than that. 33.
What?
33.
What?
3, 3, as in 3 times 10 plus 3. Okay? Now, how is that possible? Well, it's called a binary search algorithm, and this is the hallmark of exceptionally efficient and yet intuitive algorithms. Okay? It's very easy to understand. I don't even need to write the pseudocode for everybody to understand the approach of the problem. So imagine this. I have a huge stack of cards, 7 billion plus items, right? Huge stack. And I have one value to search for in the entire stack of cards. What I'm going to do is I'm not starting from the beginning. I'm not even starting at the end. I'm not even looking at either end. I go to the right. I go right at the middle of the entire stack. I pull that card out and I do the comparison. Let's say it doesn't match. Well, when something doesn't match, it can either be greater than or less than, right? Which means I can either toss away the first half of the stack or the second half of the stack. Is that making any sense? Yeah. Okay, so let's say I toss away the top half of the stack. I look at the bottom half of the stack. What do I do to that?
Well, the next one right
I do the same thing to it, right? It is now a smaller stack. I go to the middle of that stack. I do the comparison, and now I can throw away either the top or the second half of this smaller stack, which is half the size of the original stack. In other words, every comparison will divide the number of cards in the remaining stack by 2. Each time I'm cutting it in half. So the question is, how many times do I have to cut 7 plus billion in halves until I get down to a single item and I can confirm that item is not in the array? What math function do you use to determine the number of times? It's not square root. Somebody mentioned square root. It was has to do with power. Okay, but it's the opposite of power. Logs, exactly. Okay, so what you do is you look at the log of a number. So in this particular case, okay, I can show you exactly how to do it in the spreadsheet. Spreadsheets are very useful. It's really your best friend in math, computer science, and science classes. Okay, so we have 7 plus billion. Let's say 8 billion. Okay, 8 billion is 8 followed by 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So what we want to do is I'm just going to do this step by step instead of jumping steps. So I'll insert a row. This is our n. So what we'll do is we'll do a natural log of n. And it gives me 22 point something, but that by itself is not very meaningful, because I also have to do the natural log of 2, and that would be ln2, and then we can come up with the actual number of comparisons, because that would be this number divided by that number is 32.89, but you cannot have like 0.89 of a comparison. You always have to round up or take the ceiling of that function. So that means we need 33 comparisons to confirm that an entry is not in a directory that has 8 billion items. What if world population suddenly doubles again?
66.
How many comparisons do I need? 34. Do you see the power of the search algorithm? Because every time the number of entries in the array doubles, you only have to add one more comparison to the whole thing. Okay, so that's a very good example of a smart algorithm versus algorithms that just go linear. Okay, the linear search algorithm they're not very efficient. Do we have any questions about the math behind the whole thing? No questions? Okay.
Why are you dividing it by ln2?
Sorry?
Why are you dividing by the natural log of 2?
Because these both are using e as the base of the log. So this number is not telling me the number of times that I have to compare, because it's not okay. The other way to say this is 2 to the power of this number is going to be this number.
Right.
Because 2 is the base of everything that we are talking about here.
Where
Yeah.
zeros are not
Yeah. So e to the power of 22.8 is 8 billion, but 2 to the power of this number is also 8 billion. So that's why we have to divide it by the base of 2, by the log of 2, so we get the number of comparisons. In base, yeah. Because it's binary, every time we are dividing by half, and that's why it's divided by 2. Okay? All right. So now that we have this, in our thoughts, let's think about why this is so important. Okay? If someone doesn't know about this approach and use linear search, that will take up to 7 billion comparisons to confirm an item is not in the array. Okay? Because you guys already mentioned that. The question is, why is it important to understand this type of thing when you are a software engineer or someone who makes use of algorithms? It doesn't have to be the case where you come up with the algorithm. It only has to be the case that you are using a particular algorithm. So to make that obvious, I'm going to give you an example. Okay? So let's say a software company is downsizing. Okay? So me and Pat, okay, are the only 2 people left in the company as software developers, and the company could only keep one of us. Okay? So definitely a bad scenario. And worse than that, my boss says, well, let's have a programming competition. Whoever comes up with the fastest algorithm or give me the result the quickest will win the competition and gets to stay with the company, and then the other person will have to pack up and go. Okay, is that okay? Now, my boss didn't say the most efficient algorithm. My boss says the quickest answer from the computer. Now, I'm at a slight disadvantage because I'm the old timer of the entire company. I joined the company about 13 years ago, and I have never upgraded my computer. What kind of computer did we use 13 years ago?
I can't even remember. 386.
Commodore 64.
Sorry?
Windows 98.
Windows 98, but what kind of processor are we talking about?
EM2.
Sorry?
Celeron.
Pentium 2? Well, do you guys still remember Moore's Law? M-O-R-E, Moore's Law? What does it say?
Technology doubles.
The speed of a computer doubles every 18 months, not 2 years. Okay? So how many 18 months do we have? Let's make it 12 years, which rounds off nicely. How many 18 months do we have in 12 years?
8.
Exactly 8, because it's basically 12 divided by 1.5. 18 months is 1.5 years. So we have 8. So let's just say that Pat is the latest addition to the company, and he or she, that's why I use the name Pat, has the fastest computer available today. 2 to the power of 8 is 256 times. In other words, Pat's computer is 256 times faster than the computer that I'm using. And my boss is saying the competition is based on what? Response time. Okay, so I'm at a huge disadvantage here. Are we getting that point across? Because my computer is a whole lot slower. So now, my boss says, okay, let's see who can come up with the conclusion. Okay, I give you a table, an array to search from, and you have to tell me whether an entry is in the array or not, which is something that we have been doing for the past few weeks. Okay, Pat is so confident that Pat just looked up in Wikipedia and picked the first and easiest algorithm to implement, which turned out to be the linear search algorithm. I did a little bit more research because I knew that I was at a really big disadvantage, and I picked binary search. Let's see what's going to happen. I'm going to use a different sheet here. So on one column, I'm going to indicate the number of elements in the array, and one column will use Pat's computer, and the other column will use Pat's computer. Okay. When there's only one entry in the entire array, how many comparisons do I need to confirm that an element is not in the array? One. Okay. How about Pat's computer? One. Okay. But this one is not exactly one, because you remember my computer is a lot slower. So if we use Pat's computer as a base, the time that I will take, okay, so time that Tech needs to take to come up with an answer is actually this number times 256, because there is the time factor of 256, because my computer is a lot slower than Pat's computer. Pat's computer is just 1, which is just the scale, just the same as that number. So Pat comes back and say, "Ha, Tech, get ready to pack and go away, because I'm winning big time here. Okay, my time is 256 times better than yours." And then I tell my boss, well, let's try an array of 3 elements. Well, there are reasons why I go to 3 instead of 2. With 3 elements, how many comparisons do I need? Well, let's take a look at this. 3 elements. The first one I compare is this one. After one comparison, I have only 1 element left. So I only need 2 comparisons to confirm that something is or is not in the array. Okay, so Pat's computer needs 2 comparisons. Pat's computer, on the other hand, will require up to 3 comparisons, because the key or the value that we are looking for can potentially be greater than the last element of the entire array, so there's no easy way to get out early. But even so, Pat looks at my algorithm and look at Pat's computer and say, I'm losing even more, because I used to, the gap was only 255 time units, and now it is 509 units of time. In other words, it seems that he's pulling away, or he or she is pulling away, and I'm just struggling behind. And I said, well, boss, let's give us another chance. Next number will be, guess what? 7. Why 7? Well, think about this, okay? There's a certain pattern to it, okay? There's a certain pattern to it. This is 3, right? What is 7? 7 is the same thing repeated here, but with one thing in between. So the first comparison is to compare this thing in between, and then after the first comparison, I got 3 elements again. Okay? In other words, every time I'm just multiplying the number that I had before and then add 1 to it. Because the one additional one is the one in between, then after the first comparison, I get the same number as the one before. Okay? So with 7, I need 3 comparisons. Pat's algorithm can take up to 7 comparisons. So when you look at the time, Pat is laughing his way through the whole thing, because it seems like his or her time is even better now. Because if you look at the actual distance, the actual delta between using time units, Pat's solution is actually pulling away. It's getting even faster compared to mine. Is that making any sense? Okay. We can actually just visualize that, right? We can just say the delta is this number minus this number, and you can see that number is increasing. Okay, roughly proportional to bar A bar, but not exactly. Okay. No, excuse me. It's not proportional to bar A bar. It's actually proportional to tax number here. Can someone guess what the next number is going to be? 15, exactly. The actual equation is, and I'll need 4 comparisons. It's actually 2 to the power of my comparisons minus 1. That's the equation. Now, Pat's, the number of times Pat's computer needs to compare is really just bar A bar, which is 15 in this case. The times and the rest, pretty easy. We'll just do the same calculations. So it will take 1024 units of time for my algorithm to come up with a conclusion. It will take 15 units of time for Pat's computer to come up with an answer. And guess what? The difference is even bigger now because it's up to 1,009 units of time. My boss is definitely getting a little bit annoyed here and say, Pack already, you're going away. And persistent as I am, I'm just saying, well, let's double the size again. Let's see what happens, right? And by this time, the entire company is watching. So my boss cannot just call security and have me removed because everybody wants to see what's going to happen next. So we'll just go ahead and see what happens next. We're starting to see something that's troubling. I think Pat is starting to feel a little bit of pressure here because the lead is actually not increasing anymore. Okay, the lead is actually increasing, but if you look at the first derivative, the derivative itself is not increasing, or the second derivative is actually decreasing. It's a negative number. For those of you who take calculus, you know what I'm talking about. Okay. So I keep saying, let's double the size again because I'm still losing, right? My boss at this point is saying, Tech, you're such a sore loser. Okay, we'll just go ahead and double this, so that we can confirm you are not only the loser, you're the sore loser too. Okay, so my boss is actually in the game now. 63, 127, and the delta is getting bigger still, right? Oh, I think Pat is starting to have a little bit of anxiety here because it's not changing anymore. The delta is now staying the same. Guess what the next entry will indicate? It's actually lower. Okay, so the lead of Pat's computer is now lower. Now you have to remember, we are not comparing by the number of comparisons. We are comparing the actual real time of how long it takes to make the conclusion. Okay, and I'm using a computer that is 256 times slower. Okay, let's look at the next entry. It's dropping some more, and you can see the speed of dropping is increasing. So at an array size of 4,095 items, I'm leading. Not by a whole lot, but definitely leading. Pat is not convinced. My boss is not convinced, because he just said that I was a sore loser, right? So now now he wants to find out what's going to happen when we keep doubling the number. Let's find out. My lead is increasing. Not only is it increasing, it's increasing rapidly. Okay? So at the end of the day, not only am I keeping my job, not only Pat is leaving, my boss is leaving too. Because somebody reported this to the board of directors. My boss is the CEO. The CEO can still be fired, right? You guys remember how Apple fired Steve Jobs?
Yeah.
And replaced him with Now replace him with the head of Pepsi or Coke. I cannot remember which one. Pepsi? It was Pepsi, right? Yeah. That basically ruined the company until Steve Jobs came back.
Hope staying out in the middle of things.
Well, what happened here? Why did I win?
You only had to do it one more time versus they had to do it, however, every time it doubled, they had to double the number of times they did it.
Exactly, because Pat may come back and say, "Oh, but Tech is cheating because he has the top of the line of computer, 12 years ago, and I have kind of like medium of the line of computer today. Boss, I need a hexa-core computer to beat Tech's algorithm." Do you think that's going to help?
No.
It will only help to move the break-even point later. That's all it's going to do. Okay, it will not win because the shape of the curve has not changed. If you plot the log of a number versus the number itself, the number itself is linear. Okay, one is linear, which is just a straight line. What does the log curve look like? It's a curve, right? It's a curve that looks like this, depending on the constant, right? You can compress or stretch out the curve, but it doesn't change the shape because the further it gets, the closer it is to a straight line. It's never a straight line, but it gets close as the number gets bigger and bigger. So that's what we are looking at here. This is how much real time it takes, and this is the size of the problem, which is bar A bar in our case. This is called the time complexity of an algorithm. Now, you don't have to understand exactly how it is derived, but you do have to pay attention when you have to pick an algorithm to solve a problem, because it can mean whether you can keep your job or whether you get fired. Okay? Now, do we actually see something like this when we look at Wikipedia? Because I don't want to invent my own algorithm and figure out the time complexity of my own algorithm. So we'll look for, let's say, bubble sort. Okay, bubble sort, which is a very common sorting algorithm. We looked at this already some time ago, and I think that's when we talked about nested statements, structured statements. And when you look it up, it always tells you the worst case performance, best case scenario, and you only worry about the worst case scenario because nobody really cares about the best case scenario. It's big O of n squared. What that means is the execution time is proportional to the number of items in the array squared. Okay? Now, it only says proportional. It doesn't give you the actual constant, because the actual constant depends on what computer you're using. If you're tracing it by hand, it will be very slow. When you use a hexa-core computer to do this with a really fast clock speed, it'll be really fast. But all you're changing is just the constant, but not the shape of the curve. The shape of the curve in this case is a square. It's a parabola. Now, what about some other search algorithms? Can we do something better than this? Well, there are actually quite a number of sorting algorithms that can beat bubble sort. One of these is called merge sort, which is a very strange and yet elegant type of sort algorithm. So we'll take a look at this. We won't even look at the pseudocode, but what we'll do is just to look at the worst case scenario. The worst case performance is proportional to n log n. N in this case is bar A bar. In other words, the number of elements in the array. Which one is better? N times log n or n times n is better? N times log n is better. Okay? So that means if I have to choose a sorting algorithm, I would choose merge sort instead of bubble sort, because bubble sort has a time complexity of n squared, and merge sort has a time complexity of n log n. Now, why would anyone? Well, if this is so easy, why do we even talk about bubble sort and insertion sort and all the other inefficient sorting algorithms? What do you think? Because those sorting algorithms are easy to describe. They're not efficient, but they are easy to describe. I'll show you exactly what I mean by that. When you look at the merge sort algorithm, this is one half of it, and this is the other half of it. Okay? It's not very long, but when you look at the actual complexity or the conditional statements inside the loop, and stuff like that, it's actually kind of complicated. Bubble sort, on the other hand, is this. This is it. And that's why bubble sort is used a lot in a class such as this one, because it's a very easy algorithm to understand, but it's not very efficient. It has fewer number of lines to specify the logic, but it takes a lot longer for large arrays to solve the problem. Are we doing okay so far? Separating the number of lines and the apparent complexity in terms of algorithm, and separate that from the actual amount of time that an algorithm takes to execute. We doing okay? All right. So what we'll do next is to look at some other problems. Okay? Have I talked about NP complete in this class? The traveling salesman problem? Yeah? Okay. So that's also another application or another reason why you have to study boring stuff like time complexity, because sometimes you have to pick the right algorithm to stay employed, because your algorithm is actually faster. And sometimes you also need to keep your job because there are no faster algorithms in existence, and you have to prove it. In the case of the traveling salesman problem, is exactly that. Okay, your implementation has a time complexity that is big O of n factorial, which is really slow. But you can prove that nobody up to this point could solve that kind of problem with a more efficient algorithm. In other words, you can tell your boss, the chances of you hiring somebody else who can do a better job than I did is next to none. So therefore, you justify your existence, your employment, because nobody can possibly write an algorithm that is faster. Are we doing okay so far with the rationale of understanding time complexity? Okay. Now, sometimes or one of these days, if you stay on the computer science track, you will hear this term, NP complete. You can go ahead and look it up on Wikipedia. I'll just kind of describe what it means, just in very loose and not very in definitive terms. We'll talk about what N stands for and what P stands for. N stands for non-deterministic, and P stands for polynomial. I won't ask you questions like this in the test, so you don't have to write it down. Just kind of get a basic understanding of this, and because you will see this again, if you're in computer science. Non-deterministic is very easy to understand. How many cores do we have in the latest type of consumer-grade processors?
10.
Okay, let's say 10. Non-deterministic means as many cores as you want. Okay? And it takes 0 time to spin off a new core. There's no cost associated with starting a new core or a new thread that can execute truly in parallel with everything else. Now, that's a pretty magical machine, I think. Right? But even with a machine like this that has an infinite number of cores, it will still take some time that's a polynomial of the size of the problem to solve a problem. So in this case, polynomial can mean bar a bar to the power of 1. That's a very trivial polynomial, but nonetheless, it is still a polynomial. It can be to the power of 2, to the power of 4, 6, and whatnot. As long as the power itself is a constant and it has bar a bar as a base, it is a polynomial-based algorithm. So NP means that with a machine that has an infinite number of cores, it will still take an amount of time that is a polynomial to the size of the array to solve the problem. The word complete is a little bit beyond the scope of this class, but basically we have a whole family of problems that can be transformed from one to the next. And so they're all considered equivalent to each other. If you can solve one efficiently, you can solve all the other ones efficiently. So NP complete has to do with, whether your problem, the problem that you are solving, is within this entire family of problems or not. Because if your problem is within this entire family, that means if it is not possible to solve it efficiently, it's not possible to solve your problem efficiently, and vice versa. Are we doing okay so far with these terms? NP complete to date is considered intractable, which means you can solve the problem. It takes a finite amount of time, but the amount of time is just so long that it is not a practical algorithm. Are we doing okay so far with this? Okay. So just remember the concepts of time complexity and why we have to understand time complexity. In this class, we're not going to analyze why the time complexity of bubble sort is n squared, or why merge sort is n times log n. We just have to understand the basic idea so that you are aware of time complexity as one thing that you have to use to determine which algorithm should I use. My dean has just walked out. He's supposed to do my evaluation today, and you guys are supposed to fill in some questionnaires. So let me go ask him whether he wants to come back. See if he's waiting outside. So he might come back maybe next class to give you the evaluation. He has to do this is called a workstation evaluation, which means he's sitting back in the back of the classroom to observe the way I teach the class. Now he could have watched the YouTube clips too, right? And all the ones that I've recorded over the years. That will give him a lot of data points. Too much. But then he can calculate the standard deviation and all the other stuff, statistics. Let's see how long Tech uses to cover this particular topic over the past 3 years. All right, so getting back to the search algorithm, the binary search algorithm. Okay. Before we write the algorithm, we have to understand how it works and make sure that we can actually do it by hand first. So we'll go ahead and use a spreadsheet to kind of illustrate the concept. And I'm not going to list the array elements or the index here. I'll just list the values. It only works on sorted arrays. It doesn't work on unsorted arrays. So we'll just go ahead and put some kind of random-ish values here. I need one more to make it even. So that's 455. Okay. So we have an array here. I'm not even indicating the index here. What is the first number I should compare to? I will let you guys pick what number we are looking for. Pick one that you think is tricky.
900.
900. Okay, let's pick 900. Okay, so 900 is the value that I'm looking for, or to see whether it is in the array or not. What should I compare 900 to the first time?
16.
To 16, which is right in the middle. Okay. 16 is less than 900. Okay, we know that. That's pretty easy. But as a result of 16 being less than 900 and knowing the array is sorted in an increasing order, what can I confirm, or which part of the array can I toss away?
The top.
The top part. Because if 900 is less than 16, if 900 is greater than 16, it's also going to be greater than everything before 16, because the array is already sorted, it's confirmed. Yep. So that means I can cross this out, cross this out, cross this out, and 16 itself is also crossed out. I have only 3 elements left that can potentially have the value of 900. Within these 3, which one do you think I should compare? I should compare to 102 and have the same conclusion. So out of this conclusion, these I know already, but this is the new addition, and so is this one. I have now only 1 element left. This is also less than 900. So now I have just crossed out every single item in the entire array, and I can come to the conclusion that 900 is not in the array. Okay. All right, so that kind of works out. Let's try something else. Okay, let's try something trickier. Let's try something like maybe 15. Do you think 15 may be a little tricky? It's kind of right in the middle, but it's not there either. Okay, so let's try 15 and see how that works out. Well, it doesn't really change, which number I compare to, because I always pick whatever is in the middle of the remaining part of the array. So in this case, I will still be comparing to this, but 16 is greater than 15. So which part of the array can I toss?
Lower.
The lower portion. Okay, so we'll toss away all this stuff. And then of the 3 remaining one, I would use this one for comparison. And 2 is less than 15. So that means I can toss away this one and this one itself. I only have one element left, which is 5 itself. 5 is also less than 15. So that also confirms that I can toss away these. And everything that I tossed away before, I already tossed away. So there's nothing left after the third comparison. Okay. Are we doing okay so far with manually tracking how binary search is done? Okay, we're doing okay with that? Okay. Unlike the previous search algorithms, this one requires us to kind of keep track of which portion of the array may still contain the value that I'm looking for. Before, I look from the beginning to the end, so I'm just moving the quote-unquote bookmark of which part is already searched. But this time, that portion can shrink from the top. It can also shrink from the bottom. So we'll keep that in mind. Excuse me. So what we'll do is I'm going to write the algorithm, but also in stages. And make sure I save the file first to this folder. This folder right here. This is the algorithm design part. Is how do we get started with writing an algorithm. This is a search algorithm. And then we go back to our manual example. And we say, do you think this is repetitive? Am I doing something over and over again? Am I applying the same kind of logic repeatedly? Yeah. Okay, so that's good enough for me for the first revision. So in the first revision, I would just say that there's some kind of loop involved. And do we ever exit from this loop here? Do we ever come to a conclusion and get out of the algorithm?
Yes.
Yeah, we do. Okay, so that means there's an exit condition. When do we get out of the algorithm? It's a search algorithm, so with all search algorithms, we go out by 2 different reasons. Yep.
A equals A bar, A in parentheses I.
Mm-hmm. Okay.
Or K does not equal A parentheses.
Okay, so you're already thinking way ahead of time because you're thinking in terms of array elements and comparison operators. I am still in the stage of doing something like this. You can get out when an element matches the value. Okay, because if I find one element that matches the value I'm looking for, it's time for me to get out because I can confirm it is found. What is the other reason I can get out?
Confirm it's not there.
When I can prove it's not there, right?
Right.
Okay, then I can confirm or confirmed that the value is missing from the array. Is that okay? Okay. So this is awfully vague because I'm not telling you exactly how it's done. I'm just telling you that conceptually, this is how I can get out. Do you think this is important? This step is very important because it's already telling you something that you know that you did not know before. Okay, we're already stating that this is a loop. There are 2 conditions that can get us out of the loop. One is to confirm that I just got it, I just found it, and the other one is I confirm that the value cannot be in this array. Okay, now how I can do that determination we'll talk about later. All right, so let's go ahead and copy and paste this. This is going to be my revision 2. Now, revision 2 is going to be more specific to the binary search algorithm because you might remember that we started with something like this with the linear search algorithm as well. Because every search algorithm is going to be a loop, and it will exit depending on whether you found it or not in the array. So in the second revision, this is where the quote-unquote magic is, because it's really hard to describe the process to come up with this particular refinement. The refinement has to do with how do we keep track of which part of the array can still have the element that I'm looking for. Let me just go ahead and use a color coding method to indicate which part of the array may still have the value that I'm looking for. So before the first comparison, the entire array may contain the value that I'm looking for, because I cannot confirm or toss away any parts of the array. So I'm just going to format the cells here and pick a background color to indicate that the entire thing may have the value that I'm looking for. After the first comparison, I have already eliminated these 4 as potential elements. So the remaining part of the array will be these 3. After the second comparison, I'm down to 1 single element that may still have the value that I'm looking for. And after the third comparison, there's nothing left. There's nothing in beige anymore, and that confirms that no part of the array may contain the value that I'm looking for, and I can exit the loop because I know it is not in the array. Is that making any sense? Okay. The second test case has a significance because it shows that it's not just we are pushing the first part of the range. We can also shrink it from the bottom. Okay. First thing is the entire array may contain the value that we are looking for. After the first comparison, this time we're shrinking from the bottom and not from the top. But the second comparison will shrink from the top but not the bottom. And then after the third comparison, there's nothing left to compare. I confirm that the entire array cannot have the value that I'm looking for. So if you just focus on the beige portion, that's what we need to keep track of. Okay? We can no longer use a single variable that we usually call I to keep track of the boundary, because that's only one number. It can only move in one direction. In this case, we need 2 numbers because they can move in different directions. Is that making any sense? Okay. So what we need here is to indicate something like that. Okay. We need to keep track of which part of the array may still have the value that we are looking for. Okay. It's an observation based on what we did by hand. And I'll just make this its own revision because the actual representation. We'll go to the next one, which is Rev 3, revision 3. Okay. How do you think would be the best way to keep track of which portion of the array may still contain the value that we are looking for? We can use a single variable to keep track of one end. So to keep track of both fronts, what do we need? 2 variables, right? But this time, I'm going to use B and E for beginning and end. So in here, I will just say B is the index of the first element that may have the value, and E is the index of the last element that may have the value. I'm using 2 indexes or 2 numbers, 2 variables. One to keep track of where does the portion start, and the other one to keep track of where does it end. Is that making any sense so far? Okay. If that is the case, well, I'll just call this another revision because I'm starting to make this algorithm a little bit more concrete. Okay, if B is the beginning and E is the end, how do I determine which element I should be comparing to for a particular iteration? Think about it.
Difference between B and E divided by 2.
The B plus E, the whole thing divided by 2. It's just the average.
Yeah.
Yep. Okay, very good. So that means, when we compare this value, it's really comparing. Okay, so we'll need one more variable. K is the value that we are looking for. A is the array. Okay, so with K and A introduced, I think we kind of have a rough idea of what to compare here. In other words, how do we confirm that an element is already matching the value? Well, maybe it looks like this. Okay, we are confirming something in array A has the value of K, but the index is the average between B and E. So I'll just kind of write it down like this. I know sometimes it doesn't work out, especially when B plus E is an odd number. It doesn't seem to work out because I'll get a fraction. But in terms of concept, this is the concept. I'm just going to capture the concept first and then refine it later. But is that kind of working out for you guys? We are looking at the middle part and say, okay, if that's matching, then we are good to go. Otherwise, we might have to do something else. Okay? So we'll just keep it the way it is like this. We have 30 seconds. We can go through one more revision before we go. Okay, so we'll go to revision 6, and then we'll continue on next Tuesday. Okay. The other part has to do with this, okay? If A bracket blah, 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 okay. I'll just write this much. This is all getting captured, so you don't have to copy this frantically. Okay, so what we have to think about here is, okay, we know which element we're comparing. The question is, what do we do if they don't match? Okay, we know what to do when they match because it's, okay, we can get out right away. But if they don't match, one will throw away one half of the array, the other one will throw away the other half of the array. So we kind of have to think about which half we're throwing away, and then which one, B or E, should be modified, and how. Okay? So I'll just leave the algorithm like this, and we'll continue this on next Tuesday. You can read the notes ahead of me and actually read the solution, but I think it's not as much fun reading the solution than to coming up with the solution step by step.
Have you graded the test already? Have you graded the test already?
No, I have not. In fact, I forgot to pass the roll sheet also. It's okay.